Hi students, welcome back again to this course, An Introduction to Mechanical Engineering. I am Professor Yao. Case Study 1, Internal Combustion Engine. Internal combustion engine. The keywords: internal combustion engine, gasoline, diesel, ethanol, or propane, a mixture of fuel and air. In the engine's combustion chamber. As you know, automobiles, motorcycles, aircraft, ships, pumps, and electrical generators. Computer models of internal combustion engine. The perspective of fuel economy, power to weight ratio, noise, air pollution, and cost. The design terminology and the energy principle behind 4-stroke and a 2-stroke engine. The back and forth motion of the piston. Internal combustion engine. The internal combustion engine is a heat engine that converts the chemical energy stored in gasoline, diesel, ethanol, derived primarily from corn, or propane into mechanical work. The heat that is generated by rapidly burning a mixture of fuel and air in the engine combustion chamber is transformed into rotation of engine's crankshaft at a certain speed and a torque. As you know, the application of internal combustion engines are wide and varied, and they include automobiles, motorcycles, aircraft, ships, pumps, and electrical generators. Mechanical engineers develop extensive computer models of internal combustion engines, and therefore a single engine is even built. Performance will be analyzed from the perspective of fuel economy, power to weight ratio, noise, air pollution, and cost. In this section, we discuss some of the design terminology and energy principles behind 4-stroke and the 2-stroke engine. The main elements of the single-cylinder engine are the piston, cylinder, connection rod, and crankshaft. Those components convert the back and the forth motion of the piston into the crank's rotation. As fuel burns, the high pressure that developed in the cylinder push the piston, move the connecting rod, and rotate the crankshaft. The engine also contains a means for fuel and fresh air to be drawn into the cylinder, and for the exhaust gas to be vented away. 4-stroke engine cycle. The keywords: the cross-section, 2 valves per cylinder, draw-in, the byproducts of combustion, an intake of exhaust valve, cam, Otto cycle, intake stroke, compression stroke, power stroke, and exhaust stroke. Four-stroke engine cycle. The cross-section of a single-cylinder four-stroke engine is illustrated in Figure 7.15 at each major stage of its operation. This engine has two valves per cylinder, one for drawing in fresh fuel and air, and one for exhausting the byproducts of combustion. The mechanism that causes the valve to open and close is an important aspect of this type engine, and the Figure 7.16 depicts one designed for an intake or exhaust valve. The valve closes as its head contacts the polished surface of the cylinder's intake or exhaust port. A special shaped metal lobe called a cam rotates and controls the opening and closing motion of the valve. The cam rotates in synchronization with the crankshaft and ensure that the valve is opened and closed at precisely the correct instant relative to the combustion cycle and the piston's position within the cylinder. Otto cycle. Four-stroke engine operates according to a continuous procedure called Otto cycle that comprises four full strokes of the piston within the cylinder, or equivalently two complete revolutions of crankshaft, referring to the sequence of the piston positions. The four stages of the cycle operation proceeded as follows: intake stroke, compression stroke, power stroke, and an exhaust stroke. Two-stroke engine cycle. The keywords: two-stroke engine cycle, springs, camshafts, cams, or other elements of a valve train. The transfer port, uncovering or sealing. The exhaust port, intake port, and the transfer port. Downstroke and upstroke. Oil sump. Lubrication. Two-stroke engine cycle. Figure 7.18 depicts the cross-section of an engine that operates on two-stroke engine cycle. In contrast to its four-stroke cousin, this engine has no valve, and hence there is no need for spring, camshaft, cams, or other elements of a valve train. Instead, a two-stroke engine has a passageway called the transfer port that connects the crankcase and the cylinder. The engine operates on the principle that fresh fuel and air can flow from the crankcase through the transfer port and into the cylinder. As it moves within the cylinder, the piston itself acts as the valve by covering or sealing the exhaust port, intake port, and the transfer port in the proper sequence. This type of engine operates by using the principle of crankcase compression. The two-stroke engine completed a full cycle for each revolution of the crankshaft, and the power is therefore produced during every other stroke of the piston. Kirk engine cycle, as shown by the sequence of events in Figure 7.19. The Kirk cycle operates as follows: downstroke and upstroke. Two-stroke and four-stroke engine each have their own advantages relative to their four-stroke counterpart. Two-stroke engines are simpler, lighter, and less expensive. In a two-stroke engine, the spent exhaust and the fresh fuel air gas mix unavoidably as the new change flows from the crankcase into the cylinder. For that reason, a portion of unburned fuel is present in a two-stroke engine exhaust, and that leakage contributed both the environmental pollution and the reduced fuel economy. In addition, because the crankcase is used to store fuel and air between cylinders, it cannot be used as an oil sump, as is the case in the four-stroke engine. Lubrication in a two-stroke engine is instead provided by the oil that has been premixed with the fuel, a factor that further contributes to its emission and environmental problems. Homework: write hinting or keywords and submitting them to Coach Facebook. Just do the online quiz and see you next time.